So today's going to be fun because we're going to go back and do integration stuff. So we're going to start by sort of saying, okay, what's our goal? And we're going to do something very simple right now. Our goal is just simply to say, let's talk about area. Now, you can do a lot more with polar coordinates than just talking about area. But for the more, you'll do that in Calc 3. So for right now, the only thing we're going to work on is area today. On Monday, we'll talk about length. It turns out that there's a very beautiful formula for that. All right, so now we have to think about, well, how do we find area? And if you think back to our simple case, or maybe I shouldn't say our simple case, but what we've been doing before, where we had y as a function of x. Well, so if you have y as a function of x, what we do is we say, well, we'll plot the function, and now if I'm going from a to b, the basic idea is to find a little tiny rectangle and approximate that area. Now you might say, well, why are we doing rectangles? So the way that the calculus works is it says the following. We're breaking things up into small pieces. In particular, we're breaking our inputs up into small pieces. So what was happening is the reason we got rectangles is we had this small perturbation down here, which was our small change in x, our dx. We said, well, let's look at what happens in that small bit of change in our dx. Well, what lies above it is something that's a very thin shape and very tall, and except for the top, it looks really like a rectangle. Now we're in polar coordinates. So polar coordinates means that we're going to switch our thinking. So we're not thinking of y as a function of x. We're now going to think of r as a function of theta. And what happens here is we have some curve coming around here. R equals f of theta. And we're going from some angle here, I'll call this angle alpha, to some other angle over here, we'll call this angle beta. So we're going from angle alpha to angle beta. Now we're going to do the same thing. We're going to say, well, I'm going to break my input up. And the input are the angles. So I'm going to say, well, let's see what happens when I have a small perturbation. Well, so what happens is I'm coming out from the origin, and I form this sort of shape here. And what is it? Well, what it is it's a little bit of a wedge. It's a very, very thin triangular wedge. You know, if you were probably you might have done this when you were kids and you were told that you had to share the cake with some siblings, you would make sure to cut just the tiniest possible slice for your sibling and a much larger slice for yourself. That tiny slice for your sibling, that's the kind of thing we're talking about. Very, very small wedge. All right. So what do we need to understand? Well, we need to understand the geometry of wedges, or what's said here, pi slices. So it's actually very simple to figure out. So what we have here is we have a circle, and our goal is how much area is there in here. So we should think of this angle on the inside as some small change in theta. So I've cut my angle, and there's some small change in theta. And we do these ratios. We say that the area that we're after over the total area, so I can think of this as like a percentage. What percentage does that area take up of the whole thing? Well, that's equal to the ratio of the angle, the delta theta, over the full revolution. So again, it's a percentage of how much of all the way around do you go. These two percentages should match. So that's why we set them equal. Now we clear our denominator, multiplying both sides by pi r squared. And so our area is 1/2 r squared delta theta. All right, so now we're ready to put it all together. Once we know how to find the area of a small slice, we say, well, what we're going to do is we're going to take our curve. So our curve, this is our curve here. This is a polar curve, r equals some function of theta. And what we do is we're breaking up our piece by sort of just going up into various slices. So we're breaking our shape up into slices, and we're saying, well, look, each slice we can approximate by a pi, a wedge. And this is sort of the result if we break it up here into 6 wedges, where what we've done is the angles here are all equal. So we've split our angles up so they're equal. Of course, the shape is various, they go out various distances. And you can see it's not always the best estimate because you can see that we're missing gaps. These gaps here are being missed. And on the other hand, of course, we also have some pieces which are being overcounted, So it's not perfect. But if you look, it's not so bad. Well, how do you do better? And the answer is the way you get better, the way you fix these errors or make them smaller, is you get to more wedges. And if you look here, you start to see that the errors, the amount that we're off by, starts to get smaller and smaller. So in the limit, we're going to get close to the right answer. So now we have our technique. Our area is we add up over all the wedges, because that's the idea of integration. Break things into parts and add them up. How much is in each part? Well, it's 1/2 the radius squared. So the radius is how far out you go, and you go out to the function. So it's a function of theta squared times your change in your angle. Now we make our pieces get smaller and smaller, and our summation becomes an integral from our starting angle to our ending angle, from alpha to beta, of 1/2 our function of theta squared d theta. So, well, what do we do? Well, we just have to make sure, find the correct angles. Because you have to know where to start and where to stop. Oftentimes, you look at things where do things intersect. If you want to know where two things intersect, you set them equal to each other. And then you solve. And be ready. We're going to be doing trig. There's a lot of trig involved because a lot of curves in polar coordinates are described in terms of trigonometric functions. So be careful that you understand your trig identities. And in particular, you need to know your power reduction identities. So let's just remind ourselves what they are. Okay, cosine squared theta, what does that equal? I'll give you a hint, there's an over 2. 1 plus cosine 2 theta. Okay, sine squared theta. 1 minus cosine 2 theta over 2. And those are the two important ones. Now, of course, you can do things like sine theta times cosine theta is sine of 2 theta over 2. Know that secant squared is tangent squared plus 1. Sine squared plus cosine squared equals 1. And hopefully we know all of these. So let's go ahead and do an example. So, find the area inside the curve r equals 2 times 1 plus cosine theta. And we'll give you the picture. And if we ask you to find the area of something on the exam, we'll give you a picture so you can have this as a guide. All right. Well, what can we do? Well, our general formula is that we have that the area is equal to the integral alpha to beta of 1/2 our function of theta squared d theta. So let's start to talk about alpha and beta. What should we choose for alpha and beta? So 0 has been suggested. 0 is positive x-axis. All right, so that's a good choice for where to start. Where do we stop? Okay, so there's been two suggestions. One is that we should go to 2 pi, which works great. Another suggestion is, let's use symmetry. Because this curve has symmetry. If we use symmetry, where can we go to? Pi. We can go to pi, but then what do we do? Multiply by 2. So let's use symmetry, because I think it's important to sort of start getting to the idea of using symmetry. Okay, so pi, by the way, is out here. This is pi. So we're going to have 2 integral 0 to pi 1/2 times 2 times 1 plus cosine theta squared d theta. In fact, we've now done, in some sense, the hard part. We set it up. Well, what can we do? The 2 and the half cancel, so that's nice. We should square this. So this is integral 0 to pi of 4. And if we multiply that out, that's 1 plus 2 cosine theta plus cosine squared theta. The 1 is fine. We can integrate that. The 2 cosine theta, no problem. And cosine squared? Power reduction. So for 1 plus 2 cosine theta plus 1 plus cosine of 2 theta over 2, because this is the power reduction we just talked about a few moments ago. Hasn't changed since then. I'll go ahead and multiply the 4 through. So integral 0 to pi 4 plus 8 cosine theta plus 4, and then divided by 2 makes that a 2. So you get 2 plus 2 cosine 2 theta d theta. And we probably should have been smart and said, well, look, 4 and the 2, let's just put those together and make it 6. Okay. And now we're ready to integrate. The integral of 6? 6 theta. Good. And remember, it's 6 theta because we're integrating with respect to theta. That's what the d theta means. Integral of 8 cosine theta. 8 sine theta. Integral of 2 cosine 2 theta. Sine of 2 theta. And then we're going to evaluate that from 0 to pi. When you plug in pi, what do you get? Well, you get 6 times pi. Sine of pi, 0. Sine of 2 pi, 0. Plug in 0. 6 times 0, 0. Sine of 0, sine of 0, 0. That's it. That's the answer, 6 pi. So that's how much area is in this shape. And if you look at this process, it's not so bad when you express this in terms of polar coordinates. You have a fairly nice technique. If you vaguely recall, we actually did a form of this curve in Cartesian coordinates. And the expression was terrible. You'd never be able to work with it. But it just says, look, the right problem needs the right technique. And so if you have something that's described in terms of polar coordinates simply, then work in polar. If you have something that's described simply in terms of Cartesian, work in Cartesian. Now, you can have the case when you're going between curves. So you're going from an outside curve to an inside curve. And we can talk about the area that's between them. All right, well, that's not really any different than a lot of the things we've been talking about. So we've been talking, for example, the washer method. We said, hey, we're going to find sort of the big volume. Then we're going to subtract out the small volume. And that'll be the volume. So same idea here. So if I'm looking for the area, I'm going to take the larger piece, subtract the smaller piece. And what I like to think of is the f of theta here. This is the further away, the outside, and this is the closer, the inside. So you take whichever one is farther, subtract whichever one is closer. So I think it's good to go through and do an example. So let's find the area inside the unit circle and outside r equals 1 minus cosine theta. So the unit circle, that's easy to spot because it's the one that looks like a circle. That was sort of the clue about which curve it was. By process of elimination, the 1 minus cosine theta is this curve right here. It's actually one that should be a little bit familiar. We talked about it last time. So we have the area that's been shaded. Okay. Now, what comes next? Well, we need to decide on our bounds. What should our bounds be? Someone suggesting 0, which is over here, to pi over 2. Now, what's special about that? Well, for one thing, there's symmetry. So we'll double our answer. But what else do we need to do? Well, what's special about pi over 2? We should at least take a second to talk about why pi over 2. What's happening at pi over 2? It's where the intersection occurs. Now, in this case, the picture kind of gives it away. But we're going to see cases where the picture doesn't give it away. So maybe we should talk about how we get it. So let's talk about the unit circle. We need to write that in terms of polar coordinates. In polar coordinates, what does the unit circle become? R equals 1. Because the unit circle consists of all the points which is a distance of 1 away. So when you think of r is your distance from the origin. So if I want all the points that are distance 1 away, I want to say, well, I want everything where r equals 1. So that's the unit circle. So that's actually something we have to do in this problem. We have to write both the curves in terms of polar coordinates. So if we didn't know where they intersect, and again we know because we can see pictures and we're pretty good at looking at pictures, we would do the following. We would set the two curves equal to each other. 1 equals 1 minus cosine theta. We would come to the conclusion that they'd intersect when cosine theta equals 0. And then we say, aha, we know about cosine. And the first time that that happens is at pi over 2. So, okay, so that's how we would do it if we were going to do it, but we don't need to. Okay, so let's work on setting this up. So our area, it's going to double 0 to pi over 2, because we're using symmetry. Then we take the formula, 1/2. Now, I claim that we are in this setting, although it may not seem like it when you look at this picture. The problem is that if you look near 0, it doesn't feel like we're going from an outer curve to an inner curve. But don't just look near 0. So pick an angle, and what's happening as you go out? Because you should always think of, in polar coordinates, I'm always coming out from the center and going in some direction. So you pick an angle, and you head out. And what happens is, at first, you're in a little bit of white space, and then you hit a curve. And now you're keeping track. See, before you hit the curve, you're like, I don't care. Ah, I hit a curve. Okay, got to pay attention. And then you hit that, and now you don't care anymore. And so we are in between two curves. Which curve is the outer curve? The one that's furthest away. It's the unit circle, which is 1. So the one that's furthest away is the 1. So we're going to take 1 squared. And then we're going to subtract which curve is the inner curve, the one that's closest. Yeah, the other one, 1 minus cosine theta. So 1 minus cosine theta squared. So that's our setup. Good. And now we're ready to go. Well, nice news. Again, 2.5 cancel. Not everything will be symmetrical, but a lot will. And when you have symmetry, you should use it. Okay, so you have 0 to pi over 2. Well, we should probably square these things. 1 squared becomes? Yeah, that one was easy. Minus, what does 1 minus cosine theta quantity squared become? 1 minus 2 cosine theta and plus cosine squared theta. Good. Now you'll notice I'm using advanced point-saving technology called parentheses. Because when you have that minus sign, a lot of people forget parentheses. And then they get to the end and they're like, how did I end up with a negative area? You forgot your parentheses, that's why. So be smart. Use parentheses. Now, we're already going to anticipate that we're going to need to do power reduction. So we'll replace that cosine squared by 1 plus cosine 2 theta over 2. And let's see, what do we have here? Well, we have integral 0 to pi over 2. So remember that the minus goes all the way through here. And you get the 1 minus 1, so that's gone. Minus 2 cosine, so that's positive 2 cosine theta. And you get minus coming through here, so that's minus a half cosine 2 theta. d theta. All right, now we're ready to integrate because everything's nice and clean. Integral of 2 cosine theta? Two sine. Integral of a half. Half theta. Integral of a half cosine 2 theta. Sine of 2 theta, and what's the coefficient? 1/4. Where's that 1/4 coming from? Well, that 1/4 is a combination of two things. It's a combination of the 1/2 that's already there, and then we have to, accommodate for this 2 on the inside. So there's another half that comes in, 0 to pi over 2. All right, now we plug things in. So 2 times sine of pi over 2, what will that be? be 2 minus a half times pi halves. Pi over 4. And then we have sine of pi, because 2 times pi half. Sine of pi? 0. Okay, 0. Sine of 0? 0. 0. Sine of 0 is still 0. So that's it. Everything else is 0. So there's our answer. 2 minus pi over 4. All right. Good. Nice. All right. Time to try some more fun examples. Find the area outside the unit circle and inside r equals 2 cosine of 3 theta. And it's been conveniently drawn for us. Now, probably we should do a couple things. We have the unit circle. What does that become in polar coordinates? It becomes 1. All right, so we translate that. Now the next thing is we have to decide, well, how many integrals are we going to do here? Should we do one for each piece? Because there's 3 pieces in this picture. And the answer is no. Because we can see that there's symmetry. There's this nice rotational symmetry. That happens a lot in polar coordinates, that you get some type of symmetry going in. So how many integrals should we just do? We should do 1 integral. Now, let's focus on doing an integral near here. And in fact, I would strongly encourage you, this is a good rule of thumb, that if you can get 0 involved in a problem, you should do it. So I would say, let's not even do a whole leaf. Let's start here at 0, and we'll just do a piece of it. So suppose that we just want to find that. If we find that much, what do we need to do to get our final answer? Multiply by 6, right? Because if we double, that's 1 leaf, there's 3 leaves. Okay, so that's our goal. So the question becomes, what's this angle? All right, now we have to think about it, because it's not so obvious. So we start, well, this angle comes because of that intersection. So if we're doing intersections, we're going to set the 2 curves equal. In other words, we're going to set 1 equal to 2 cosine of 3 theta. So that's our goal. When does 1 equal 2 cosine of 3 theta? Well, that's the same as saying that cosine of 3 theta is equal to a half. And now we ask ourselves the question, when does cosine equal a half? Don't worry about the 3 theta, just the question, when does cosine equal a half? We have some people saying pi over 3. I also heard of pi over 6. It's probably one of those two. Which one is it? It is pi over 3, yeah. Now you're probably thinking, that does not look like a 60-degree angle, because it's not a 60-degree angle. So what's happening is the 3 theta, that's our input, has to equal the first time that our input gives us a cosine of a half is when our input is pi over 3. So we're setting our input, 3 theta, equal to pi over 3. So what does that say about theta? Pi over 9. Divide both sides by 3. Which means that this is a 20-degree angle, pi ninths angle. Now, you might be nervous and say, I don't know my trig values for pi ninths. Well, forge ahead. You probably won't need it. All right. So you might get some strange angles. These angles don't always have to be just, ones that we know off the top of our heads. But that's all right. So we're going to have our area is going to be 6, because we're just doing a piece of it. 0 to pi over 9. And now this is a case where we're going between 2 curves. So we're going to have to do inside minus, our farthest away minus our closest away. And if you're not sure, again, I'll just use another leaf. You just think about what's happening. As you come out, you hit, and then you keep moving until you go. Which curve is the outside, the one that's furthest away? The 2 cosine of 3 theta. So that's the one that comes first. 2 cosine of 3 theta squared. Subtract, which one is the inside, the one that's closest? The 1. So subtract 1 squared. All right, now we're good. We've done the hard part. And the rest is just fun integration. Okay, so let's see. 6.5, we can make that a 3. Integral 0 to pi over 9. And now we have 4 cosine squared of 3 theta minus 1. Well, cosine squared of 3 theta, what would that become? 1 plus cosine 6 theta. Yeah, be careful. You just need to double the angle inside. So in this case, our angle on the inside is 3 theta. So doubling 3 theta gives us 6 theta. All right. So now we're going to clean this up a little bit. So we get 3 integral 0 to pi over 9. So notice there's a 4 out in front. So this is being multiplied by 4, and there's really a minus 1. So we have the 2 goes into the 4, leaving us with 2. If you multiply that through, we get 2 times 1, which is 2. And then there's a minus 1. So if we put all our constants together, we'll end up with 1. 4 and 2 is 2 still, and that's multiplied by cosine 6 theta. Okay. D theta. Are we okay? For fun, I'll go ahead and multiply the 3 back in. You're probably thinking, that does sound like fun. Or you're probably thinking, why are you doing that? Well, I anticipate that something's about to happen, which is interesting. So let's integrate. Integral of 3? 3 theta. Integral of 6 cosine of 6 theta. Yeah. See here the 6 was very convenient. So sine of 6 theta. And now we need to go from 0 to pi over 9. So 3 times pi over 9, what will that be? Pi thirds. Sine of 6 pi ninths. Well, we have to think for a second. 6 pi ninths. What's another way to think of that? So sine is 6 pi over 9. That's the same as sine of 2 pi over 3. All right. What is sine of 2 pi thirds? So in case you're wondering where that fits in a unit circle, so sine of 2 pi thirds is over here. It's 120 degrees. So what is the sine of 2 pi thirds? Square root of 3 over 2. So we're going to add that. Plus square root of 3 over 2. Plug in 0. We're going to get 0. And sine of 0 is 0. And that's our answer. Pi thirds plus square root of 3 over 2. Probably wouldn't have guessed that when we started. But the nice thing is we don't have to guess. We can do the math. And the math will take care of us. And life is good. All right. Well, we're just going to keep doing problems until we run out of problems or run out of time. But I suspect we'll run out of time before we run out of problems because there's so many fun problems that we can do here. Okay. Find the area inside the curve r equals 2 sine theta plus sine of 2 theta. That's the picture. I think that's a better looking heart than the cardioid curves, but all right. Now we have to think about what to do. Because this curve, it kind of intersects itself, so we've got to be careful. If we were to integrate from 0 to 2 pi, we'd run into certain obstacles and challenges. What should we do?
Subtract the inside.
So you want to subtract the inside?
Because we'll double count if we do normal integration.
Well, so if you did 0 to 2 pi, so what would happen is you get 0, then pi over 2, then here would be pi. And then from pi to 2 pi, it'd actually be negative, so you trace out the second part. So yeah, there is a problem of like, how do we account for the inside? And then, of course, the counterpoint to that is, why should we bother accounting for the inside? Let's not worry about it. What can we do? We can go 0 to pi over 2. Let's think about where that takes us. Now, it's not so clear, but it is the case that at 0, we start at 0. And that what happens is, from 0 to pi over 2, we're going to be following along here. And then we'll stop here at pi over 2. So if we go from 0 to pi over 2 out to the curve, we would be getting this part. That's what going from 0 to pi over 2 would do. Now, that's actually a pretty good part, because what can we do with that? We double it, and now we have our answer. So, our area would be double what we get from going to 0 to pi over 2. Do I need to worry about an outer curve minus an inner curve? No, I don't. Because my curve starts at the origin, or sorry, my region starts at the origin. In essence here, the inner curve is r equals 0. So we just have to go out to the curve squared. So this double is because of symmetry. Then the formula says that there's a half. And a lot of people forget that half. So we take off points. So don't forget that. 2 sine of theta plus sine of 2 theta squared d theta. All right, well, this is, we're getting really good at our trig integrals, which is great. Okay, so let's square this out. What do we get when we square this out? The first term? 4 sine squared theta. What's the middle term? 4 sine theta sine 2 theta. And where's the 4 coming from? Well, if you do a plus b squared, there's 2ab, and 2 times another 2 makes 4. The last term? Sine squared of 2 theta. Okay. So now we have 3 pieces to have to figure out how to integrate, which is going to be like, All right, well, let's just go through these one at a time and talk about what we can do. The sine squared theta, what can that become? 1 minus cosine 2 theta over 2. No big surprises. That's just double angle. Let's skip ahead. The sine squared of 2 theta, what can that become? Yeah, another similar formula. 1 minus cosine of 4 theta over 2. Now just remember the double the inside. So double 2 theta becomes 4 theta. And now the middle term. Now this one is kind of, makes you think, sine theta, sine 2 theta. Now there's multiple ways to do it, but most of them involve trig identities which we probably haven't memorized. So we want to use trig identities which we have memorized. So we start rummaging through our facts. What are trig identities which might be useful here? Yeah, so probably the best one. See, the real problem with this part is that you have a theta in one of your signs and a 2 theta in the other sign. It's like comparing apples and other types of apples. You don't want that. You want them all to be the same. So you can use your power reduction, which really has a double angle. Sine of 2 theta, this is 2 sine theta cosine theta. So how do we use that? Well, we're going to write this as, since I have a 4 sine theta here, this will become 8 sine squared theta cosine theta. Now, let's clean this up. 0 to pi halves. I'm going to get 4 times a half is 2, and then there's another half over here. So that'll become 5 halves, so the 2 and a half. Then I get minus 2 cosine 2 theta, which is from this term right here, minus a half cosine of 4 theta, which is from the term on the end, and then plus 8 sine squared theta cosine theta. I claim we're ready to go. Let's go through these one by one. What's the integral of 5/2? 5/2 theta. Okay. All right, good. We're warming up. Don't worry. We'll start challenging ourselves as we go on. Integral of minus 2 cosine 2 theta. What will that be? Minus sine 2 theta. We have to divide by the 2, which cancels with the 2 in front. What's the integral of minus 1/2 cosine 4 theta? Minus 1/8 sine of 4 theta. Okay. We've had 30 seconds to stare at the 8 sine squared theta cosine theta. Do you know the integral of this one now? Eight thirds, yes, of sine cubed theta. Now, some of you are like, yes, that's exactly what I was thinking. And some of you are probably like, what? Okay, so where is that coming from? If you think about what we have here, sine squared theta, cosine theta, this is sort of one of our happy places when it comes to trig integrals involving sines and cosines. Because one of our exponents is an odd exponent. In fact, it's even better than that, it's to the first power. So what you could do is you could do the following. Secretly, what we do is we say, let u equal sine theta, du is cosine theta d theta, and what we have is the integral of 8u squared du. And now that's an integral that's not bad. It'd be u cubed over 3. That's where the 8 thirds is coming from. U cubed becomes sine cubed. And at this point, if you don't feel comfortable doing that without writing it down, go ahead and write it down. But this is probably one you could do, writing it down. All right, well, now we have to evaluate. So, good news. When we plug 0 in, what's going to happen? You're going to get a whole lot of 0. So we just have to plug in our angle pi halves. 5/2 times pi halves is 5 pi over 4. Then we're going to get a sine of pi, because we're going to double pi halves. Sine of pi? 0. This will be sine of 2 pi, which is 0. This will be sine of pi halves. And then we cube 1, we get 1. So plus 8 thirds. So 5 pi fourths plus 8 thirds. And that's the answer. All right, good. Let's try another one. This is a big picture. Kind of a snowman type shape here. Find the area inside both of the curves. R equals 2 minus sine theta, R equals 3 sine theta. Well, there's a couple things we should probably figure out. Which curve is which? Because you have two curves. You have this curve, which looks a bit circlacious, and this curve, which is a little less circlacious, more oblong. Which one do you think is which? Sorry, what? The bottom one is what?
Bottom one is r equals 3 sine theta.
So you think this one is r equals 3 sine theta?
Yeah.
Bold choice, bold choice. Could be. You have a 50-50 chance. Is there a reason that you think it's 3 sine theta?
Yeah, because before, sine theta is always between 0 and 1. So 1 times 3 should give you r equals should equal 3, which is greater than 2 minus sine theta, the distance between 0 and 1.
Well, but remember, sine theta, the reason it was, well, sine is bounded. The biggest they can get is 1. The smallest they can get is negative 1. 2 minus minus 1 is also 3. So it can also get 3 away.
Never mind.
I'm not saying you're wrong. I'm just gotta. All right. Let's use a little bit of logic here. We know that sine theta can't be big. In fact, that's one of the advantages of sine. We like sine because it stays more or less bounded between negative 1 and positive 1. What's true about 2 minus sine theta? Where can it go between? Wait, where can it go? So 2 minus sine theta, what's the smallest 2 minus sine theta can get? 1. What's the largest it can get? 3. So if I look at the graph of 2 minus sine theta, can it ever hit the origin? No, because 2 minus sine theta always stays a little bit away. The closest it ever approaches is 1. Now, between which one of these two curves does one of them never get close to the origin? Yeah, the bottom one never approaches the origin. So this curve here is the 2 minus sine theta. The curve 3 sine theta, can that get close to the origin? Yes, in fact, it starts at the origin, because if you put in theta equals 0, it starts there. So this is the top curve, r equals 3 sine theta. Now, on exams, we do tend to label things. But now you have something even better than a label. You have an interactive person to go, which is even better. Okay, so now we know our curves. What's the next thing we should try to figure out? We should work on our bounds. Okay, so to figure out our bounds, what should we do? Okay, so people are saying, well, 0 and pi halves and symmetry. Okay, sure. I totally buy into that. We'll double that. Is there anything else we need to know? We need to know where they intersect. Yes. So we need to know this angle. All right. So how do we find that? Well, we set the curves equal. That would be when 2 minus sine of theta equals 3 sine theta. Well, move that across. 2 equals 4 sine theta, or sine of theta equals a half. What angle gives us sine of theta equals a half? Pi over 6. Well, many angles do, but the first angle that does it is pi over 6. So that says that this is pi over 6. Okay. Next question. Which curve is on the outside?
2 minus sine theta.
It's a trick question. It depends on where you're at. This is not take an outside squared minus an inside squared. What's happening is if your angle is low, you go out to the 3 sine theta. If your angle is high, you go out to the 2 minus sine theta. So what we have is we really have two separate problems. We have to say between 0 and pi 6, we got to find our area out to this curve. Between pi 6 and pi halves, we got to find our area out to a different curve. So that means we get to do twice as much work, which is good, because the more we work, the better we get. All right, so we set ourselves up. So remember, we're going to double because of symmetry. So we start with our first piece, double, 0 to pi 6. We have a 1/2. And what's our curve? It's the 3 sine theta. So if we're between 0 and pi 6, the curve we hit when we come out is the circle, r equals 3 sine theta, plus double pi 6 to pi halves, and 1/2. And now, what do we hit? 2 minus sine theta. All right, so the hard part about this problem is getting the setup. Hopefully the rest of it will be pretty quick. So we'll try to speed up here. The 2 and the halves, the 2 and the half, they cancel. So we get 0 to pi over 6, 9 sine squared theta, d theta, plus integral pi over 6 to pi over 2 of 4 minus 4 sine theta plus sine squared theta, d theta. And of course, we're going to replace sine squared by 1 minus cosine 2 theta over 2. And we're going to do it in both places, 1 minus cosine 2 theta over 2. So this is integral 0 to pi over 6, 9 halves minus 9 halves cosine 2 theta, plus pi over 6 to pi over 2. We have 4 plus a half, which makes that 9 halves, then minus 4 sine theta, and then minus 1/2 cosine 2 theta, d theta. So 0 to, we integrate 9 halves theta minus 9/4 sine 2 theta from 0 up to pi over 6 plus 9 halves theta minus, well, what's the integral of 4 sine theta? We haven't actually done the sine today. I don't think we have. Yeah, it'll be a plus 4 cosine theta minus 1/4 sine of 2 theta from pi over 6 to pi over 2. And we plug it in, and lo and behold, we get answer. Now, of course, on an exam, you should actually probably write down what the answer is. But that's the process. And you know what? We should be a little bit more careful here. We should really get an answer. We should find this out. All right, because, hey, we have the time. We have the technology. So what do we end up with? We ended up with 9 halves theta minus 9/4 sine 2 theta. Evaluate that from 0 to pi over 6 plus 9 halves theta plus 4 cosine theta minus 1/4 sine of 2 theta, and that's from pi over 6 to pi over 2. So we plug these in. We're going to get 9 halves times pi over 6, then minus 9/4 sine of pi thirds. We'll come back and simplify that. Subtract, plug in 0, 0 and 0, so let's subtract 0, plus 9 halves times pi over 2, plus 4 times cosine of pi over 2. Well, cosine of pi over 2 is 0. Sine of pi is 0. Subtract 9 halves times pi over 6. And then we're going to get plus 4 cosine of pi over 6 minus 1/4 sine of pi over 3. All right. Well, the nice thing that happens here is you see this part right here? Cancels with that part right there. So, gone. Nice. And certainly the zeros, nice. That's good news. Other good news. Sine of pi thirds is actually something we know. Sine of pi thirds is root 3 over 2. So, that's root 3 over 2, that's root 3 over 2. Cosine of pi 6 is also root 3 over 2. So, what do we have here? We got a bunch of terms. So, let's just be careful here. So, let's see. Things that have a root 3 attached to them. So I'll pull those out. We have a minus 9/4 times a half, so minus 9 over 8. That doesn't have a root 3. This has a root 3. And be careful with this minus. This is going to come in. So that's a minus 4 times a half, which makes that minus 2. And then minus minus makes a plus 1/4 times a half. So that's a plus 1 over 8. And then plus 9/4 pi. Now, minus 9/8 plus 1/8, if you combine those together, that gets us up to a minus 8/8, also known as minus 1. So, minus 1 from those two, minus 2 makes minus 3. So we get 9/4 times pi minus 3 root 3. And that's our answer. Okay, well, that one took a lot of work. That's a much simpler one. Of course, we want the credit, right? And if you want the credit, you do the work. You do the work. Now, let's try another one. Find the area inside the bean shape, this shape right here, given by r squared equals sine theta plus cosine theta. It's kind of unusual. We have an r squared here. Now, in fact, that makes it kind of a little bit simpler. Because if you think about the way we talked about our area formula, see, our area is the integral from your starting angle to your ending angle of 1/2. We usually say f of theta squared, but really, this is r. This is what f of theta is, d theta. So if I have an expression for r squared, well, that's great. So now the question becomes, well, what are my angles? So one way we can think about it is to say, well, what angles do we go between? So that's, we can think of, we start here, move around, and come back. Now, why don't we have anything down here? Well, it might be that sine theta plus cosine theta is negative down here. For instance, plug in pi. Sine of pi is 0, cosine of pi is negative 1. Can't have r squared be negative 1. So now the question is, well, when am I here? Well, what I really need to know is, when does sine theta plus cosine theta equal 0? Now that's the same as saying sine theta equals negative cosine theta. If you divide sine over cosine, tangent theta is negative 1. And that happens at negative pi over 4, plus 180 degrees away from that. So that's over here at 5 pi over 4. Wait, is that? No, 180 degrees. Ah! I know how to add 180. That's like adding pi. 3 pi over 4. There you go. There you go. So, we get integral negative pi over 4 to positive 3 pi over 4 of 1/2, and r squared is sine theta plus cosine theta d theta. So, this becomes 1/2 integral of sine is negative cosine. Integral of cosine is positive sine. And then we're going to go from negative pi over 4 to positive 3 pi over 4. Now we just have to be a little bit careful. At 3 pi over 4, cosine is negative root 2 over 2. Sine is a positive root 2 over 2. Alright, so that's when we plug in 3 pi over 4. Minus, at negative pi over 4, cosine of negative pi over 4 is root 2 over 2. Sine of negative pi over 4 is negative root 2 over 2. And if you work out all the signs, you see that all these minuses go away. So you have a root 2 over 2 plus a root 2 over 2. So this becomes a root 2. This also becomes a root 2. Now you have 2 of those. So this is 1/2 times 2 root 2. The 2 and the half cancel. So our final answer, square root of 2. Nice. Beautiful, clean answer. We like it when the math works out to to a nice value. And one more. Don't worry, you'll probably get more chances. After all, we do have that exam coming up in the near future. Find the area in the shaded region below for r equals sine of 1/3 theta. Now this is kind of interesting. See that sine of 1/3 theta? That means you have to go around, not from 0 to 2 pi. 0 to 2 pi is not enough. You got to go around multiple times. That 1/3 kind of throws it off. So let's see if we can kind of trace where things go. Let's start with saying theta equals 0. Well, that would be sine of 0. So at that point, we start there. So this is where our curve starts. And now, as we move up, we get out at theta equals pi halves, we're going up. So we'll be up to sine of pi 6, which is about a half. And so that says we go here. So this is from 0 to pi halves. Now, as we keep going, by the time we get to pi, we're over here at sine of pi thirds, which is root 3 over 2. So this is at pi over 2. This is at 0. Here's at pi. And by the time we get all the way over here to 3 pi over 2, we're downstairs. All right, no big surprises. Now, if we were to continue, by the time we get to 2 pi, we're here. Now notice something here. When we're at 2 pi, we're not the same as when we're at 0. So even though the direction, theta equals 0, theta equals 2 pi, are the same, the r value can be different. We're at sine of 2 pi thirds. And then when we come up here, this would be 5 pi halves. And then when we come over to here, that's at 3 pi, we're back to 0. So it takes us 3 pi to fully go around this curve once. And of course, if we keep going, then we'll swing around it again. Now, how do we find this? Well, one thing we can do is we can think of it as sort of two pieces. What happens from 0 to pi over 2 will be here. And then the other part is what happens from pi over 2 to 3 pi over 2. That'll be here. This part. Now, of course, I'm not drawing this properly. If I was talking about drawing this properly, thinking about it in terms of polar, you always think from the center. So you would draw that, and for this other side, you would draw from the center out. So that's what you should be drawing if you're doing this in polar. All right. Well, so we see, great idea. If we go from pi over 2 to 3 pi over 2 and double it, that gives us our full shape, but then we need to pop that part out. So we go from 0 to pi over 2, double that, and subtract it off. So, our plan. We're going to say, we're going to take the big piece, so 2 by symmetry, integral pi over 2 to 3 pi over 2 of 1/2 out to the curve. So we're going out to sine of 1/3 theta squared d theta. That would be if we had just the outside part and we left the inside in. So now we've got to take out the inside. So subtract 2, 0 to pi over 2, 1/2 sine 1/3 theta squared d theta. That's that little tiny piece, the double by symmetry. And now we're going to take it out. So the 2 and the half cancel in both cases, which is good for us. So we really have a sine squared of 1/3 theta. So what do? Well, we do power reduction. So this, that's not going to work very well. Let's try a better color. This term right here, sine squared of 1/3 theta, will become 1 minus cosine 2/3 theta over 2. And same thing, 1 minus cosine 2/3 theta over 2. So we're actually doing the same integral. So that's going to be good because it means we're not going to have to think twice as much. We just have to do it twice as often. So the integral of a half theta. Then we get the integral of cosine is still sine, so that's still going to be a minus. The inside stays alone. Now we think of the coefficient. There's a 2/3. When we bring it out, it's going to come out as a 3/2. And there's another 2. So that'll be a 3/4. And that's going to be from pi halves to 3 pi halves. Subtract. Same integral, so it's the same antiderivative. So 1/2 theta minus 3/4 sine 2/3 theta from 0 to pi over 2. So we start working our way through our values here. So we're going to get 1/2 times 3 pi over 2, that's 3 pi over 4. And then, what do we have? We have 2/3 times 3 pi over 2. Well, the 2 and the thirds and the 3 over 2 cancel, so it's just sine of pi. And sine of pi, 0. Good. Some good news for us. Okay. All right. So that's plug in 3 pi over 2. Subtract, plug in pi over 2. Well, that's 1/2 times pi over 2 is pi over 4. Minus. Okay, now we get sine of 2/3 times pi halves, which will be pi thirds. What's sine of pi thirds? Sine of pi thirds, square root of 3 over 2. All right, so that's what we get. And, well, don't forget, I almost did that 3/4. You always check. So times 3/4. Good. Check twice, and then you don't have to fail the class. Okay, so that's that one. Minus, okay, so we're going to plug in 1/2. 1/2 times pi half, so that's pi over 4. And then we're going to get minus 3/4. Then it's the sine of pi over 3 again. Well, we don't have to hum and haw twice. And then, okay, I'm going to use extra parentheses here. Minus, plug in 0. Well, finally, some good news. 0. 0 is very convenient. So what do we have? We have 3 pi over 4 from our first term. We have a minus pi over 4. Then we have plus 3/8 root 3. And here we'll have a minus pi over 4. And then another plus 3/8 root 3. So 3 pi over 4 minus pi over 4 minus pi over 4 leaves us with a pi over 4. Now that takes care of the pi over 4 terms. Then we have a 3/8 plus 3/8, which makes it 3/4 and root 3. And that's the answer. All right, good. Well, I mean, what do you do on these? Break it into smaller parts. Don't try to find one integral that does everything. Think about doing it piece by piece. Because one of the things that's tempting to do when you see this problem is to say, hey, you know what looks like what's happening is it looks like I have upstairs. Oh, that's a terrible picture, Steve. Yeah, I know that's a terrible picture. But okay. Well, it looks like what's happening is it's like, oh, look, I'm going between two curves. So don't I need to do an outer curve minus the inner curve? And the answer is no, that won't work. And why doesn't it work? Well, the reason it doesn't work is that these are not two separate curves. It's the same curve at two different times. And that's not the same process. So you can't just be like, oh, 1/2 f of theta squared minus g of theta squared. So you got to be careful. So the best thing to do is break things up into small parts, work on each part individually, and put them all together. And if you do that, you should be good. That's it for this part, and we'll pick it up again next time. Hope you have a good day. Bye.